Application of Faraday's law. A solenoid, having 15 turns of a copper wire, has a circular cross-section whose area is 200 centimeters square. The ends of the solenoid are connected to a voltmeter. A magnetic field of 0.5 Tesla that is perpendicular to the plane of each turn of the solenoid is placed near the solenoid. Slowly, the magnetic field is moved uniformly into the solenoid until it reaches 1.5 Tesla in 30 seconds. Calculate the EMF induced in this time interval in the solenoid.
Find the induced current if the resistance of the solenoid is 0,02 ohm.
We draw a diagram to assist us in solving this problem. We may assume that there is a bar magnet near the solenoid, where the initial magnetic field experienced by the solenoid is 0.5 Tesla. Slowly, the magnet is moved in so that the field increases to 1.5 Tesla in 30 seconds. We are required to find the induced EMF during these 30 seconds. Recall Faraday's law, which states that the induced EMF is equal to the rate of change of magnetic flux associated with the solenoid. Here, delta phi is the change in flux, that is, the difference between the final magnetic flux and the initial magnetic flux. And we know that magnetic flux is given by the following equation. Phi equals BA cos theta. The initial magnetic flux and the final magnetic flux can be calculated easily. Note that the angle theta is 0 degrees here. The area of the solenoid that is experiencing the flux is given as 200 centimeters square. We can calculate the flux through a single loop of the solenoid. Phi initial equals 0,5 times 200 times 10 to the power negative 4 times 1 equals 0,01 Weber. Phi final equals 1,5 times 200 times 10 to the power negative 4 times 1 equals 0,03 Weber. Delta phi equals phi final minus phi initial equals 0,03 minus 0,01 equals 0,02 Weber. The induced EMF is given by EMF epsilon equals negative n times delta phi over delta t equals negative n times delta phi final minus delta phi initial all over delta t equals negative 15 times 0,02 all over 30 equals negative 0,01 volt. The negative sign just indicates that the EMF tends to oppose the increase in flux. We are interested in the magnitude of the EMF, which is 0,1 volt. Let us now see how this setup generates an induced EMF. If the resistance of the circuit is 0,02 ohm, we can easily calculate the current in the circuit as current I equals epsilon over R, which equals 0,01 over 0,02, which equals 0,5 ampere.
Starting to feel it? Now go master it with Maski.